So good morning and welcome back to this NPTEL course on Cycloaddition. So the last lecture we talked about brief overview of organic reactions, pericyclic reaction, then we talked about cycloaddition, various types of cycloaddition, and we started with initial discussion of 4+2 cycloaddition, wherein we talked about what are the requirements for dienes and dienophiles to undergo normal Diels-Alder reaction. So in the last lecture I gave a few examples where we want to discuss about stereochemical and regiochemical outcome. So today we will discuss more about the stereochemical and regiochemical outcome of normal 4+2 cycloaddition reaction. So when we talk about stereochemistry, as you can see here, this reaction is between a diene having 4 carbon atoms and dienophile having 2 carbon atoms. So in the process you see a cyclohexene is being formed. Okay. If there are 2 substituents at the terminal carbon atom of the diene and then 2 substituents at both the carbon atoms of dienophile, in the product you can clearly see the possibility of 4 new stereocenters. So theoretically in Diels-Alder reaction you can generate 4 new stereocenters, and we all know Diels-Alder reaction is highly stereospecific. So whatever the stereochemistry you have in the diene and dienophile, it is retained. Okay. So that tells it is good to start with the fixed geometrical isomer of the diene and dienophile so that you can easily create a maximum of 4 stereocenters in Diels-Alder reaction. Okay. How does it happen? How does this Diels-Alder reaction? Mechanistically, if you look at the Diels-Alder reaction takes place between the diene and dienophile, and so it is by the overlap of p orbitals of diene and dienophile, and they just lie perpendicular to the plane of carbon atoms. Okay. So this is one over another. If this is diene and this is a dienophile. So when this happens, normally there are 2 possibilities. That is, if we have a diene, then the dienophile can come either from the top face or from the bottom face. For example, if you draw a diene like this, the dienophile can come either from the top face or from the bottom face. Okay. Then if the dienophile comes from the top face, it should give 1 enantiomer, and if the dienophile comes from the bottom face, it should give the other enantiomer. So in principle, if there are no chiral components present in either diene or dienophile, you will end up in getting racemic mixture. Okay. Then one can also say, when you have a dienophile, alternatively the dienophile is in a plane. Now the diene can come either from the top or from the bottom. So each one will give the opposite enantiomer and equal amount. So that is why Diels-Alder reaction without any chiral component in the diene and dienophile gives racemic mixture. Okay. Now let us see how these stereochemical possibilities. First I have drawn this diene, and this diene is in a plane. Assume that the dienophile is coming from the top face of the diene. So this will give one enantiomer. Then since this is planar, okay, the diene is in a plane, there is an equal possibility that dienophile can also come from the bottom face. If that happens, that should give the exactly opposite enantiomer. So since the possibilities are same or equal, so you will get both enantiomers in 50-50. That is why you get racemic mixture. And the other approach, as I said, is instead of keeping diene in the plane, one can also keep the dienophile in the plane. Okay, both are possible. And if you keep dienophile in the plane, now the diene can approach the dienophile from the top face, or it can come from the bottom face. In both cases, you get the opposite enantiomer in equal amount. That is how you get racemic mixture. Okay? So this concept you should understand why in a Diels-Alder reaction, when there is no chiral component in the diene or dienophile, or without using any external chiral catalyst, you always get racemic mixture. Another thing which you should know when you talk about Diels-Alder reaction, where to write wedge bond and where to write straight bonds. What are wedge bond? What are straight bonds? See, often you would have seen in the literature or in the textbook, some molecules they write like this wedge bond, where you can see the bond tapers down. And in some structures, you see it's a straight bond. It does not taper down. What does it mean? So wherever you see bonds where these bonds are tapering down, that means that is absolute configuration at that center. If it is not, and if it is straight bonds like this, that means they are relative, not absolute. I will give one example to understand better about wedge and straight bonds. See, for example, you take phenyl cyclohexene, one phenyl cyclohexene, and then do a hydroboration oxidation. So now, as you know, hydroboration oxidation is addition of water in anti-Markovnikov's fashion. So that means the hydrogen and water can come either from the top or from the bottom, keeping the double bond in the plane. So if hydrogen and OH comes from the bottom, then you get this particular isomer. Now there is also another possibility that hydrogen and OH can come from the top face. If it comes from the top face, you get this isomer. Okay. Now if you look at, since we are not using any asymmetric or chiral component, this is a racemic mixture. This is one enantiomer, this is other enantiomer. But these two substituents are trans to each other. So that is why we use these straight bonds. The straight bonds both are trans to each other but not chiral. Again, these two are trans to each other but not chiral. They are relatively trans to each other. Okay. Their stereochemistry is trans to each other but not chiral. However, if you use asymmetric hydroboration on this double bond, so depending on which reagent you use, plus or minus, the hydrogen and water can come from either alpha or from the beta. If it comes from the alpha, since this is asymmetric hydroboration, you get this isomer, this enantiomer. Now here you can see this is absolute stereochemistry. That is why you see the phenyl carbon bond is tapering towards. Likewise, you can see the hydroxyl C bond is tapering towards the carbon. Okay? And more importantly, like any hydroboration, here the two substituents are trans to each other. Okay? It's a chiral one because you are using one enantiomer of the chiral borane. And you can also write like this. Can you write like this? Here, what is the difference between these two? The tapering of this wedge bond is towards phenyl group. Likewise, here the tapering of the wedge bond is towards hydroxyl group. So, between these two, which structure is correct? This is wrong and this is correct. Why? The tapering should be towards the chiral center. So, now if you look at this, this is the chiral center, this is the chiral center. So, that means the tapering should be towards that chiral center. That is why this is the correct structure and not this one. Okay. If you want to know more about this, please go through this article in Journal of Chemical Education, which discusses such wedge and straight bonds, where to use and how to use in detail. So, now coming back to 4+2 cycloaddition. So, as I said, there are two possibilities. You have a diene, the dienophile approaches either from the top or from the bottom. First, let us assume, okay, the dienophile approaches the diene from the bottom face. Okay. So, now you have a diene and you have a dienophile. How the dienophile approaches the diene from the bottom and what are the implications? So, now first you look at the diene and you draw a circle. See, for example, you have 1,4-dimethyl butadiene. Okay. Now, can you draw a circle? Okay. When you draw this circle, you will see at the terminal carbon, there are two substituents. One is methyl, other one is hydrogen. Now, this hydrogen as well as this hydrogen, they are inside the circle. Okay, they are inside the circle. So, that is why they are called inside substituents. Whereas the methyl, both methyl groups are outside the circle. So, they are called outside substituents. So, whenever the dienophile approaches the diene from the bottom, the inside substituents of the diene will become beta. That means the outside substituents, that is the methyl group, will become alpha. So, this is when the dienophile approaches a diene from the bottom face. As I said, it is equally possible that the dienophile can approach the diene from the top face. So, what will happen? I will come back to this, how to draw this structure in the next couple of slides. So, on the opposite one, now the diene, the same thing, is flat and the dienophile approaches from the top face. So, that means here you will get exactly opposite. That means the inside substituent will become alpha, whereas the outside substituent will become beta. Okay? And the structure will be like this. Okay? So, I have written this structure. How I can write? How do you write it? Okay? Let us see like this. First, let us see the bottom face approach. So, you have written, you have drawn the diene like this, okay, and it is in the plane. Now, the dienophile approaches the diene from the bottom face. Can you draw this transition state like this? See, you can see the dienophile comes from the bottom face. When the dienophile comes from the bottom face, automatically this inside substituents will be pushed to top. Okay, when the dienophile comes like this, the inside substituents will be pushed to top. The top means above the plane. Above the plane means it is beta. Can it be drawn like this? Very simple logic. So, the dienophile comes from the bottom and these two hydrogens are pushed up, and that is how you get this product. The same thing, can it be redrawn like this? Can it be redrawn like this? So, now as I explained, what happens? The inside substituent, the hydrogen, it is beta now, and the outside substituent is alpha, provided the dienophile approaches the diene from the bottom. And you should not write like this because this is not chiral. This is not chiral. It's only relative configuration. So you should write with straight bond. Okay. The exactly opposite is the approach of the dienophile from the top face of the diene. Okay. So now same dienophile, and the dienophile approaches from the top, and that should give this compound. Okay. Now rotate this, rotate like this and 180 degree, and you will get this compound. Again you can see here exactly opposite to what you have seen. Now the inside substituent is alpha and the outside substituent is beta. Okay. So this is what you should know, that in a normal Diels-Alder reaction, in a normal 4+2 cycloaddition reaction, both top phase and then bottom phase approach are possible. That is because there is no chiral component, no steric region. So in such cases, both approaches will give 50-50 enantiomers. Finally, it will lead to racemic compound. Okay. So far we talked about symmetrical diene, symmetrical dienophile. When you have unsymmetrical diene, dienophile, then you have to know an important concept called endo and exo. So what are these endo and exo? So for simplicity, let us take only one aspect, that is your diene is in the plane and your dienophile comes from the bottom face. Okay, your diene is in the plane, dienophile comes from the bottom face. So now if the dienophile has a substituent, again then there are two possibilities. So look at this diene, the diene is in the plane. Now the dienophile has a substituent, electron withdrawing group. This dienophile either can be in this position or this orientation, or it can also be in the other orientation, that is like this. See, for example, if you take your hand, left hand, this is the double bond and this is the substituent, that is aldehyde. So now it can be either outside like this or it can be like this. If it is like this, that is leading to endo. If it is like this, it is leading to exo. So what is endo, exo means? Endo means this substituent on the dienophile is below the plane of the diene. Okay. So if you have a diene and then if you have dienophile, so this is the diene and this is the dienophile. You can see now this dienophile comes from the bottom face and this is a substituent here. This substituent is just below the diene. Substituent is below the plane of the diene. So that is endo. Now the another possibility which I said, it can be like this. This case, the substituent on the dienophile is away from the diene plane. It is away, outside the plane of the diene. So that is called exo. Okay. This is what you should understand. Okay. So once you know this, then it is very easy to draw endo and exo products. Okay. So now let us look at with three-dimensional imagination. So you have the diene and the dienophile is acrolein. So endo approach, that means, as I said, that aldehyde or any electron withdrawing substituent should be below the plane of the diene. Okay. When it approaches from the bottom face, the aldehyde should be below the plane of the diene. Okay. So this is what it is. So now you draw the bond, this is the transition state. So when you do this, you will get this product. I will leave it for few seconds. So when you do that, you can see here this aldehyde is alpha. Okay. And as I said, when the dienophile approaches the diene, these substituents, that is the hydrogens, will be pushed up. When it is pushed up, it is beta. The hydrogen will be beta. That means the other substituent on the terminal carbon, that is phenyl group, will go to alpha. So that is how you get this structure. Is it clear? Now same thing for XO, you draw the same transition state. So now if you draw it such a way, if you look at this conformation, this stereochemistry does not change, because that is already there in the diene. That is what I said. When you talk about stereochemical outcome, always the stereochemical outcome of your Diels-Alder product will not change, whether the stereochemical relationship in the diene and the dienophile will not be affected. Okay. So here the diene, that is not affected, but what is affected is the dienophile because of the orientation. This case it is XO orientation, that is why this aldehyde is beta, and same thing you can see. Okay. So there is a rule for this, that is called Alder's Endo rule. And what is Alder's Endo rule, and why you get only Endo product, or the maximum predominantly only Endo product. So if you look at the HOMO-LUMO of Diels-Alder reaction, normally for a Diels-Alder reaction to happen, HOMO of diene and LUMO of dienophile are involved in the reaction. Okay. So HOMO is, for diene it is psi 2. So psi 2 means it should have one node. You can see there is a node here, and for the dienophile it is LUMO. Okay. So it should have two nodes, okay, one here, one here. In the case of Endo product, so for example in the last example it was aldehyde, isn't it? Last example, double bond and aldehyde. So in the case of aldehyde, so you can see here there is a secondary orbital interaction between this lobe and this lobe, which actually stabilizes. So that is why, though Endo product is a kinetic product, is the major product, the secondary orbital interaction is the one which stabilizes, and you get Endo product as the major product. Whereas in the case of XO, this is away. So there is no chance of secondary orbital interaction. So that is why XO product is a minor product, and XO product can be major product only in the case of very high temperature. See why at very high temperature you get XO product. XO product is thermodynamically more stable. Okay. So when you have mixture of Endo and XO, it is a reversible reaction. Okay. So what will happen when you heat it at very high temperature, the Endo product will go back to diene and dienophile, and again upon heating you will get mixture of Endo and XO, and the process, so the Endo product will be converted into XO product only at very high temperature. Otherwise, normal Diels-Alder reaction condition, you get Endo product as the major product. Okay. To understand it better, let us look at this cube model. So what is cube model? See, first draw the cube. Okay. So we all know how easy to draw cube. So we have drawn the cube now. Okay. And when you draw the cube, what you should know is this 4-membered ring, you put the dye in. The top 4-membered ring, you put the dye in. Now, the bottom 4-membered ring, you attach the dienophile. This particular model, please assume that the diene is in the plane and the dienophile is coming from the bottom face. So now, if you look at this, as I said, in normal 4+2 cycloaddition reaction, you get endo product. That means your electron withdrawing groups here should be just below the diene, just below the diene. Okay? So now, next is just to make the bond. So when you make the bond, this is what the intermediate, okay. In this structure, you add the remaining hydrogens, because here you are not in the previous structures, you have not added hydrogen at the double bond. Now, in this structure, here you add hydrogen, okay. Then you convert that into the product, okay. This is the product using cube model. Next, what you should do, once you have this, okay, this is what you got, and see from this side. When you see from this side, this is how the molecule will look, okay. So this double bond is here. When you see from here, you can see this is this hydrogen that is towards you, so that's why it is beta. Then this hydrogen, that is this hydrogen, this also towards you, so it is beta. And in the dienophile, after the Diels-Alder reaction, these two hydrogens also towards you. So now all the 4 hydrogens are towards you, okay. So this cube model is very easy to understand how you can write the endo and exo product, okay. And you can also remove the hydrogen, you do not need hydrogen, okay. You need not write the hydrogen to show that there is hydrogen. So if you do that, and this is how your endo product will be, okay. And if it is exo, just you have to bring the 2E outside, and what will you get is then these two this will be this, correct, and that will come from isn't it? So the 2 E's which are below the diene, now it is away from the diene, so that will give you this exo product. So it is very easy to write the stereochemical outcome, that is exo endo product, if you follow this cube model, okay. So now we will stop today with 2 examples, and first assume that the dienophile approaches the diene from the bottom face, okay. So now you have this diene, okay, then your dienophile approaches from the bottom face, okay, this is what you get. And now if you write the product, what will you get? You should get so in the product you will see now this methyl is alpha and this hydrogen is beta. This is alpha, yes, this is alpha, and this carbon, that is here, your methyl is towards you, that is beta, okay. The compound, again it is racemic, Though it's chiral, it is racemic because you don't have any chiral component in diene and dienophile. Okay. Now you look at same thing, you replace it with cyclopentadiene. Okay. So cyclopentadiene and do a Diels-Alder reaction with dimethyl acetylene dicarboxylate. So what will happen? So you have cyclopentadiene and then the dienophile approaches from the bottom, and that should give you basically what you should know is this methylene group which is inside substituent, that will become beta. Okay. This is beta. These hydrogens, these two hydrogens are alpha. And if you do that with maleic anhydride, okay, you do the same thing. Maleic anhydride advantage is this is Z isomer. So now if you do this reaction, this is XO. But if you do this reaction with this transition state, now you can see this both carbonyl groups are below the diene. That means this will give the endo product. So the endo product, if you see here, it is and that's what it is. And if the dienophile is trans or E here, then you can see what will happen. It is symmetrical, does not matter. Either this ester can be here or this ester can be there. So that should lead to this product. Okay, it's a trans compound, still it's not chiral. But if you have a substituent in the diene, then you will get the corresponding enol TMS ether. Okay. So what is important is the stereochemistry of the diene or stereochemistry of the dienophile is 100% retained in the products. This is what you should remember. Okay. I will stop here and then we will discuss more about stereochemical outcome of Diels-Alder reaction, and also we will discuss more about the regiochemical outcome of 4+2 cycloaddition reaction in the next lecture. Thank you.